the technology that could navigate without GPS. Every second, billions of people depend upon signals arriving from space. Aircraft cross continents using satellite navigation. Ships follow precise routes across oceans. Smartphones calculate their position within seconds. Telecommunications networks and financial systems even depend upon satellite timing signals to remain synchronized. Yet this extraordinary infrastructure has one fundamental weakness. The signals reaching Earth are extremely faint. They can be blocked, disrupted, or deliberately imitated. That vulnerability has created a new technological race. Scientists are developing navigation systems that do not need to ask a satellite where they are. Instead, they measure motion, gravity, time, and even the Earth's magnetic field with extraordinary precision. At the heart of these systems are atoms manipulated using the laws of quantum physics. The objective is remarkable: build a machine that can determine where it is by measuring the physical world around it. Welcome to the age of the quantum compass. GPS works because satellites continuously broadcast extremely precise timing information. A receiver compares signals from several satellites and calculates how far each signal has traveled. From those measurements, it determines its position. Similar satellite constellations operated by Europe, China, and Russia form what is collectively called Global Navigation Satellite Systems, or GNSS. They have transformed modern navigation, but they depend upon radio signals traveling enormous distances before reaching Earth. Military planners have therefore spent years investigating alternatives for situations where satellite navigation cannot be trusted. DARPA's research explicitly includes positioning, navigation, and timing systems designed for GPS-denied environments. The aim is not to destroy or replace satellite navigation. It is to ensure that losing access to those satellites does not mean losing the ability to navigate. The traditional alternative is called inertial navigation. Accelerometers measure movement, while gyroscopes measure rotation. By continuously recording how a vehicle accelerates and turns, a computer can estimate where it has traveled from its starting position. The principle is used in aircraft, submarines, spacecraft, and missiles. The problem is drift. Every sensor contains tiny measurement errors. At first, they appear insignificant, but as the journey continues, those errors accumulate. Eventually, the calculated position gradually moves away from the real one. Highly accurate inertial systems can reduce this problem, but eliminating it completely is extremely difficult. Scientists therefore began asking whether atoms themselves might provide a more stable reference. NIST says atomic gyroscopes could enable accurate navigation for submarines, aircraft, ships, and satellites when visual or electronic guidance is unavailable. This is where quantum physics enters the story. When atoms are cooled to extremely low temperatures, researchers can control their behavior with extraordinary precision. Lasers can manipulate clouds of atoms and create what physicists call matter waves. By splitting and recombining those waves, an instrument known as an atom interferometer can detect extraordinarily small changes in acceleration or rotation. The basic idea is surprisingly elegant. Instead of relying entirely on a mechanical sensor that slowly develops errors, the system uses the predictable properties of atoms as a reference. Laboratory cold atom systems already provide some of the most accurate measurements available for inertial sensing, and researchers are now working to shrink these instruments from laboratory benches into compact devices capable of operating outside controlled environments. Gravity provides another possible navigation reference. Earth's gravitational field is not perfectly uniform. Mountains, underground rock formations, ocean trenches, and differences in the planet's internal structure produce tiny variations in gravity from place to place. A sufficiently sensitive quantum gravimeter can measure some of these differences. If a vehicle compares its measurements against an accurate gravity map, the pattern could help establish its location without receiving any external navigation signal. NASA is developing a space-based quantum gravity gradiometer that will use 2 clouds of ultra-cold rubidium atoms as test masses. By comparing their acceleration, the instrument is designed to detect extremely small gravitational variations. NASA's immediate objective is Earth science rather than navigation, but the same underlying ability to measure gravity with extraordinary precision demonstrates why quantum sensing attracts so much attention. The Earth's magnetic field offers another potential reference. Our planet is surrounded by a magnetic environment shaped by its core and by magnetic minerals within the crust. Those magnetic patterns vary geographically. Extremely sensitive magnetometers can measure tiny changes in magnetic fields, providing another form of environmental information that does not depend upon a satellite broadcast. Quantum sensors exploit atomic properties such as spin, effectively using atoms as incredibly sensitive magnetic detectors. NASA already uses highly sensitive magnetic instruments to study planetary interiors and magnetic environments, while NIST describes quantum sensing as a way of measuring physical quantities beyond what conventional approaches can achieve in some applications. In future navigation systems, magnetic measurements could potentially be combined with inertial and gravitational information rather than relying upon any single sensor. Timing may prove just as important as position. Modern satellite navigation works partly because atomic clocks aboard satellites keep extraordinarily accurate time. Quantum technology is also improving clocks that can operate locally. The more stable an onboard clock becomes, the longer a vehicle can maintain accurate timing without repeatedly checking an external signal. That matters because positioning, communications, and navigation are deeply connected to time. DARPA has spent decades investing in technologies intended to provide positioning, navigation, and timing capabilities when GPS is unavailable. The future quantum navigation system may therefore look less like a single revolutionary compass and more like an orchestra of atomic clocks, accelerometers, gyroscopes, magnetometers, and gravimeters continuously comparing their measurements. The attraction for defense applications is obvious. A submarine cannot rely continuously on satellite signals while traveling underwater. Aircraft operating in contested environments may encounter deliberate interference. Ground vehicles may operate between buildings, beneath dense terrain, or inside locations where satellite reception is weak. A navigation system based primarily on internal measurements would be much harder to disrupt remotely because there would be no navigation signal for an opponent simply to overpower. DARPA's robust quantum sensors program is specifically intended to move quantum sensing toward demanding defense platforms. But this reveals the biggest challenge. Quantum sensors are extraordinarily sensitive precisely because they detect tiny physical effects, and real vehicles vibrate, accelerate, change temperature, and generate electromagnetic noise. Turning laboratory precision into rugged hardware is therefore one of the central engineering problems researchers are trying to solve. The technology could eventually extend well beyond defense. Aircraft could gain an additional navigation layer when satellite signals fail. Ships could maintain more accurate positioning in difficult environments. Autonomous vehicles may eventually combine quantum sensors with cameras, radar, and conventional inertial navigation. Geological surveying could benefit from highly sensitive gravity measurements, while underground infrastructure might be detected through subtle gravitational differences. NASA's planned quantum gravity mission is being developed partly because precise gravity measurements can reveal changes associated with groundwater and other features beneath Earth's surface. Quantum sensing therefore represents more than another navigation technology. It is a new way of detecting extremely small features of the physical world that conventional instruments may struggle to measure. But there is an important reality behind all the excitement. Quantum navigation is not currently a tiny box ready to replace the GPS receiver in your phone. Many cold atom systems still require lasers, vacuum chambers, sophisticated electronics, and careful environmental control. NIST's own research program emphasizes the challenge of translating laboratory-scale cold atom instruments into compact devices through improved vacuum technology, integrated optics, and other engineering advances. This is exactly why claims that GPS is about to become obsolete should be treated cautiously. Satellite navigation is cheap, global, mature, and extraordinarily useful. Quantum systems are much more likely to strengthen navigation by providing an independent backup than to eliminate satellites altogether. The most powerful navigation system of the future may therefore be hybrid. GPS could provide regular global positioning whenever signals are available. Classical inertial sensors could track rapid movement. Quantum accelerometers and gyroscopes could reduce long-term drift. Atomic clocks could preserve precise timing. Gravity and magnetic maps could occasionally provide independent position references. Artificial intelligence could combine all of these measurements, continuously deciding which source should be trusted most. If one signal disappeared, the others would continue working. Navigation would no longer depend upon a single technology. It would become a resilient network of independent measurements, each checking the others. That broader concept is consistent with DARPA's long-running effort to develop alternative positioning, navigation, and timing technologies, rather than relying exclusively on GPS. The quantum compass, therefore, represents something larger than a better navigation device. It represents a gradual shift from signal-dependent navigation toward physical world navigation. Instead of constantly asking satellites where we are, future machines may increasingly determine their position by measuring acceleration, rotation, gravity, magnetism, and time itself. The technology is still developing, and significant engineering obstacles remain before quantum navigation becomes commonplace. But the scientific foundation is real, and some of the world's leading research organizations are actively working to bring quantum sensors out of laboratories and into practical systems. Jeep is not disappearing. Satellites are not becoming irrelevant. What is changing is our dependence upon them. And in a future where navigation must continue even when the sky goes silent, the most reliable compass may ultimately be built not around a signal from space, but around the strange and extraordinarily precise behavior of atoms themselves. If you enjoyed this documentary and want more fact-based investigations into quantum technology, artificial intelligence, advanced engineering, and the scientific breakthroughs shaping our future, please subscribe to the channel. Every week we explore complex subjects using clear language, balanced evidence, and thoughtful analysis, helping you stay informed in a rapidly changing world.